From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone. Does everyone know what tomorrow is? Maybe you don't worry about it. I don't know. Income tax day? Do you have to, graduate students have to worry about income tax day? Yeah, okay. Well, at the end of the class, I'll hand out the exams. I'll say the average for on the exam was 74. The median was 77. The highest was 100, and the lowest was 18. And maybe this is the time to comment on the final exam and how I count the final exam. If we go back and look at what I handed out the first day of class, we saw the homework counts 20%, the two exams count 40%, and the final exam counts 40%. But in addition to that, what I always do is I look at the final exam, and if you get an A in a final exam, regardless how poorly you've done during the semester, you'll get an A in the course. And so I'll give you the benefit of the doubt when it comes to looking at the final exam. Anyway, we have several topics to cover before we get to the final exam. And I guess we were talking about, a week ago today, we're talking about diffraction gratings. And I think we're looking at how much light we had in a given order. And we had a couple of conditions, a couple of types of gratings we'd looked at. First was just a binary amplitude grating. And we had the max percent of light in first order. I forget, what was that? Does anyone know? Maybe I shouldn't say percent, fraction of the instant light in the first order. Well, that was about 10%. It's 1 over pi squared. Okay. And then we had the binary phase grating. Max light in first order. Remember what that was? Well, we gained, what, a factor of 4? That was 4 over pi squared. Okay. And both of these occurred when we had a 50% duty cycle. And I guess this occurred when we had a 180-degree phase difference between, for the grating, the phase went like so. And we said the phase steps here were 180 degrees to get to 4 over pi squared. Well, there's two more gratings we want to look at, both sinusoidal gratings. First one would be a sinusoidal amplitude grating, and then the second one would be a sinusoidal phase grating. So let's go on to that. Get my paper here, right there. Okay, this is section 14.6, and it's on sinusoidal gratings. And then first part of that is 14.6.1, which would be sinusoidal amplitude gratings. And so we have an amplitude transmission here. It goes as 1/2 times 1 plus m prime, I guess I use, cosine 2 pi nu naught x. So sinusoidal amplitude grading. And with this, what we know, we get a 0 order, and we're going to get a plus or minus first order. So if we take the Fourier transform of this, I'm going to write it here at 0 spatial frequency. And then we're going to get an m prime. And I guess we could write this as e to the I and e to the minus I with a 1/2 out in front. So we get a 1/2 here. So it's a 1/4. And at frequency nu naught. And then m prime over 4 at frequency minus nu naught, plus 1 and minus 1 orders. Okay, so now we can write down the order number and how much light in each order. So, and light in order. So what percentage of the incident light's in a given order? 0 order, well, what, 1/2 amplitude, and so the radiance would be 1/4. And plus 1 order, what's m prime over 4 squared? And minus 1 order would be the same. Okay. And so what for this to stay positive here, m prime, largest value m prime can have is 1. And so the most light we can get in a given order would be when m prime is 1, and we get 1/4 squared, or 1/16. So if m prime is 1, 1/16 of light, of incident light, in plus 1 and minus 1 orders. Okay, so we get 1/16 of the light in a given order. And we have only the 3 orders. We have a 0 order and then plus 1 and minus 1. Now for the, let's go back and kind of compare this with a binary amplitude grading. And so binary amplitude grading, and we had a 50% duty cycle. We get what was 1 over pi squared and plus or minus 1 order. Now, with a sinusoidal grading, we're getting only these 0 order and plus or minus first order. Binary amplitude grading, we're getting a lot of orders. Okay? And so your guess might be, at least my guess would be, that we would get more light in the first order for the sinusoidal amplitude grading than what we get for the binary amplitude grading, because we have so many orders here. But if we look at this for a second, for the sinusoidal grading, we got 1/16 of the light in the first order, while here we got 1 over pi squared. So even though the binary amplitude grading has more orders, we're getting more light in the first order. Does that seem strange to you? Yeah, nothing seems strange to me. So the conclusion here is that this, I think it's kind of strange. So although, the binary amplitude grading has more orders than the sinusoidal grading. It has more light in the plus or minus first order. So the question might be, why is this true? Why do we get more light in the first order even though we have more orders? Does anyone want to make a guess? Well, if the light doesn't go in that order, it has to go someplace. And so maybe it's absorbed is kind of a first guess I might make. And so let's see if we can think about this for a second. What's the total amount of light through a 50% duty cycle binary amplitude grading? So how much of the instant light gets through this 50% duty cycle binary amplitude grading? Tough question here. 50%. Very good. Does anyone disagree with that? Okay. Good. People are awake. So we get 50%. Now, for sinusoidal grading, it's going to be more complicated. We're actually going to have to do some work. I don't know how much gets through, but it's 1/2 times 1 plus cosine 2 pi mu naught x. I'm going to square this. Now that depends as a function of position, so we're average over x. And see what that becomes. And so if we multiply that out, well, 1/2 squared I can do. That's 1/4. And then we get 1/4 times 2 cosine 2 pi mu naught x. That's a 1/2 cosine 2 pi mu naught x, average of that. And then we get 1/4 cosine squared 2 pi mu naught x, and the average of that. And so that's equal to, well, 1/4. Average of the cosine, 0. Average of cosine squared, 1/2. So there's 3/8. So that's our answer right there. That the total amount of light going through the sinusoidal grading is only 3/8 of the instant light, while for the 50% duty cycle grading, amplitude grading, we get 50% of the light through. And so even though with this binary grading we get a lot more orders, we still get more light in the +1 order than what we get for our nice sinusoidal grading, where we have only the 0 order and the plus or minus first order. So I always thought that was kind of interesting. And we haven't talked about holography yet, but we'll get to that later in the course. And one thing that worried the early people making holograms was that they were recording sinusoidal fringes, but due to the photographic process, nonlinearities, that they didn't end up with sinusoid. That actually it can help you and give you more light than what you would have had if you'd had a perfect sinusoid transmission here. Okay, any questions on that? Okay, we have one more grading to look at, one more sinusoidal grading to look at, and it's a phase grading. And it's a strange little creature, actually. And This is 14.6.2. Sinusoidal phase grading. So let's say now we have an amplitude transmission. Well, all the light's transmitted through, but it's going to see phase variations. And so we can write that as e to the I, guess m over 2, sine 2 pi nu naught x. So we introduce this phase variation. Which has which goes from m over 2. I was checking something in my notes. I thought maybe I'd changed something, but I haven't. To minus m over 2. Okay. So now we have to see what orders we get from this and how much light's in a given order. And just like I didn't say it before, but in the previous grading I was assuming infinite size grading, so I don't have to worry about effects of the finite size of it. And the only effects of the finite size of it would be that we would convolve each order with the Fourier transform of the aperture of the grading. So anyway, to solve this, there's an identity that we use, which is that e to the I, m over 2, sine 2 pi nu naught x is equal to a series of Bessel functions. So I'll say j sub q, argument m over 2, and then e to the I, 2 pi, q, nu naught x, minus infinity to infinity here. Summing over q. So that's summation over q minus infinity plus infinity of j sub q m over 2 of m over 2 e to the I 2 pi q nu naught x. And so if we were to take a Fourier transform of this, of amplitude transmission, what we would get then would be this series j sub q m over 2 delta of u sub x minus q nu naught u sub y. So the q here corresponds to the order number. And so q is equal to 0, of course 0 order. Interesting ones, q plus or minus 1, plus or minus 1 order. And so if we write here the order number and the value of q, I mean qth order, the percent of the incident light in that order goes j sub q of m over 2 squared. So we have to look at what these Bessel functions are to find out how much light we have in a given order. And I think I gave you a handout maybe a long time ago now, I forget. I gave you something from Mathematica that was calculating this. I'll just show the plot here. So, if we can see this, So these are the order numbers. The red here is order number 0. And the green is plus or minus 1. And the blue is plus or minus 2. And down here we have plotted m over 2. And so first off, what we can see, when m over 2 is 0, of course everything is transmitted through. Everything goes in a 0 order. As m over 2 increases, the 0 order will decrease, and a plus or minus first order will increase. Okay. And the maximum value of this comes up to about, I think it's about 34%, 33.9 or so. We'll say 34% at a m over 2 of a little less than 2. And we also see that as m over 2 increases, there's a point here which this goes to 0. The 0 order goes to 0. That's not quite the same location as where the first order is a maximum. And I just showed plus or minus first orders and second orders. There are other orders here. So for a sinusoidal amplitude grading, we had 0, plus or minus 1. Sinusoidal phase, in general, we get many orders. And as m over 2 becomes larger, these higher orders become larger. Okay. Any questions on that? Well, I thought that was, it's again a kind of interesting thing, the difference between the sinusoidal amplitude and the sinusoidal phase. Okay, and the fact that you can get zero order here by the right value of m over 2. Okay. Well, again, I'll go way back to handout you got at the beginning of the class. This was in the view graphs on interferometry. There's a couple of pages there that are kind of interesting, which are basically just summarizing the results that we found on gratings here. That we had the 4 types of gratings we looked at. We had binary amplitude, and so for this drawing anyway, this spacing is h and the width of each open area is b. We had binary phase. Okay. We had sinusoidal amplitude. And we have sinusoidal phase, where I've shown things a little bit differently here. Instead of having the phase be m over 2, I have the phase being 2 pi m over 2 for this particular drawing. And then I had the next page in this handout gave a summary. This will be kind of hard to see on the TV probably, but everyone should have a copy. Maybe not with you, I'm sure, but back in your office you have a copy, where we have written down the type of grating, the transmission, and the diffraction efficiency, and then for the first order diffraction efficiency here. And again, just summarizing amplitude, binary largest we had is 1 over pi squared. Amplitude sinusoid 1 over 16. Phase binary 4 over pi squared. And for phase sinusoidal, approximately 34%. Okay. Any questions on any of that? Okay, well that concludes our chapter 14 here on Fraunhofer diffraction. So am I safe to assume that everyone here is an expert on Fraunhofer diffraction? Okay. And I see you have handed in some of your homework for today. Okay, well, let's go on then to chapter 15, which is on optical transfer functions. And the reference that we're going to be following here will be chapter 6 of Goodman's book. So this is going to give us a way of determining how well an optical system is working. We have some object, and this object has some spatial frequencies in it, and this object is going to be imaged by our optical system, and the image is going to have some spatial frequencies in it, and we're going to calculate the ratio of the amplitudes of the spatial frequencies in the image to what was in the object, and this then will tell us, give us an idea as to how well the system is performing. We are going to do this for two cases. We're going to look at it for coherent light, and we're going to look at it for incoherent light. And we'll probably make some comments about in between here where it's partially coherent, but these are the two areas that we're going to study most closely. We're going to go through some math, again, pretty much following Goodman's book, and you probably don't even need to take notes. You can just get it right out of his book. But in addition to going through the math in his book, I want to talk physically about what's happening here. And I think you all know that I think that everything in the world is an interferometer. And I want to prove to you that a lens is nothing but an interferometer, okay? So this is my chapter where I can finally do that, okay? But we have to go through some algebra first. Okay, well, we're going to start out with a coherent transfer function. And I think, at least from my viewpoint, the incoherent one is the one that's probably of more interest to me. But the coherent is easier to look at. Sometimes it's what we're worried about. And it will lead us into the incoherent case. So, coherent transfer function. Now, when we have an imaging system, often there's some magnification between object and image, and that might make the algebra here a little bit more complicated, worrying about the magnification. And also, with an imaging system, the image is often inverted from the object. And so this inversion also messes it up a little bit, messes up the algebra a little bit. So what we're going to do here is that we're going to pick a coordinate system such that we don't have to worry about the magnification. We don't have to worry about image inversion. Okay? So pick coordinate system. Such that we do not need to worry about magnification and image inversion. Really what we're going to do here is that when we're comparing the image to the original object, what we're going to do is we're going to compare the image to the perfect geometrical image. And that way we will have taken care of the magnification problem, and we will have taken care of the image inversion. So maybe I should write that down. We'll compare image to perfect geometrical image. Okay. Okay, now we'll go to Goodman's book for a little while and go through what he has. And then we'll talk about this physically, what's happening. Well, I guess that due to the linearity of the wave propagation, we can write here that the amplitude of the image, and I guess the coordinates UV is what he is using, is equal to, we're going to convolve some point spread function, U minus squiggle V minus eta, and I guess he puts a little tilde above that. Perfect geometrical image, squiggle eta, D squiggle D eta. So, limits plus or minus infinity. So we're saying that the image here is the convolution of the perfect geometrical image with some point spread function. And this point spread function we can calculate as just the image of a point source. So H of U and V, and it's like a Fraunhofer diffraction pattern, so we have an A and a lambda and Z sub I, which we'll later not worry about. And we have some pupil function here. And for the first part, we'll assume we have no aberrations in the pupil function, and later we'll put some aberrations in. So right now, this is just setting the size of the aperture, and then e to the minus I, 2 pi over lambda z sub I. So z sub I is the distance from the exit pupil to the image here. U x plus v y dx dy. Okay, so h is just the what we'll call the amplitude point spread function, and it's what we get for the image of a point source, and so it's just a diffraction pattern produced by the optical system. Okay. Now, we have this image here. What I want to do now is look at the spatial frequency content in the image, and we're going to look at the spatial frequency content in the perfect geometrical image. So we'll define frequency spectra. Of input and output. And so for the input, we're taking as a perfect geometrical image. So G sub G, call it, F sub X, F sub Y. Take a Fourier transform of U sub G, our geometrical image. E to minus I, 2 pi, F sub X, U plus F sub Y, V, du, dV. Okay, so we have the Fourier transform of the perfect geometrical image. And that gives us the spectra of the perfect geometrical image, the spectra of the real image, G sub I, F sub X, F sub Y, is going to be the same, except U sub G will become U sub I. E to the minus I, 2 pi, F sub X, U plus F sub Y, V. Okay. So that's the spectra of the input and output. Now what we can do, we had this convolution of this amplitude point spread function. So let's take the Fourier transform of this point spread function. Of the amplitude point spread function. And so we'll call that capital H of f sub x, f sub y. Fourier transform here of h u v e to the minus I 2 pi f sub x u plus f sub y v du dv. Now, so that's the Fourier transform of the amplitude point spread function. Now back here we had the amplitude of the image was equal to the perfect geometrical image convolved with this point spread function. And so if we use this old convolution theorem that Gaskell or someone taught us, we take the Fourier transform here of both sides, and we get that Fourier transform of u sub I, g sub I, is equal to the Fourier transform of the point spread function, which is what we're calling capital H of f sub x, f sub y, times Fourier transform of the perfect geometrical image, so that's capital G sub g of f sub x, f sub y. So the spectra of the image is equal to the Fourier transform of the amplitude point spread function times the spectra of the perfect geometrical image. And this thing right here is capital H is what we're going to call the coherent transfer function. And capital H here, just writing it down in words, is the Fourier transform of the amplitude point spread function. Okay? So I'll celebrate that by taking a sip of coffee. I think they got the coffee water mixed up with the sewer water today, actually. I don't know. It's terrible coffee. But it's still better than nothing. Okay. So let's go on and look more at this coherent transfer function. So everyone has this copy down. I'll move it out of the way. Now go to blue ink. So this h of f sub x, f sub y is a Fourier transform of a over lambda z sub I, integral here, p of x and y, e to the minus I, 2 pi over lambda z sub I, ux plus vy, du, dv. Okay? So it was the Fourier transform of the amplitude point spread function, which came from just the diffraction pattern, and which was basically just a Fourier transform of the pupil function here. And so this is equal to, we have some constants out in front, which we're going to forget about, times the pupil function minus lambda z sub I f sub x minus lambda z sub I f sub y. So we're going to set these constants equal to 1 when we would normalize it. And we're going to ignore the fact that the pupil is flipped over. So ignore these negative signs in the argument of P. Okay. And what we have here is that the coherent transfer function is simply equal to the pupil function here. And we have to maybe mess around a little bit to get the units right. So the coherent transfer function is equal to the pupil function. Okay. That's kind of interesting. I even draw a red box around that, I guess. Then what we want to do is we want to look at some examples, and then we're going to try to understand why this makes sense. Okay. So a couple of examples here. Examples of amplitude transfer function. And you can probably guess that two examples are going to be a square and a circle. Okay. So let's do the square first. P of x and y. And using Goodman's notation, rectangle function of x over 2w, rectangle function of y over 2w. So the rectangle function is equal to 1 if what's inside here, well, the absolute value of that is less than a half. And so what this is a square then of width 2w. Okay. And again, using Goodman's notation, we have P of xy for the circle is circ, C-I-R-C, of square root x squared plus y squared over w. And what this is equal to 1 if this argument inside here is less than 1. If it's greater than 1, it's equal to 0. So this is a circle of diameter 2w. I don't know why he ever picked that, but 2w. Okay, so these are the two apertures. And then the transfer function is given by for the square h is rect lambda z sub I f sub x over 2w. Rect lambda z sub I f sub y over 2w. And we'll look at plots of these in a second. And for the circle, this is just going to be circ square root f sub x squared plus f sub y squared over w divided by lambda z sub I. And let's look at his pictures, and then I'll draw a one-dimensional trace here. So if we could, everyone have this written down? Everyone has a copy of Goodman anyway, I guess. So. If we zoom in here on his beautiful pictures, I think one of the bigger changes between the first and second edition of his book is he has, I guess, nicer pictures here, fancier pictures anyway. So this is just the, I mean, it's unity until we get to the cutoff frequency, and then it's 0. And the cutoff frequency here is w over lambda z sub I. And the same thing for the circle here. It's unity. It's either 1 or it's 0. So if I were to make a little, these are pretty pictures maybe, but I think I'd prefer just to have a little one-dimensional slice here. What we have is that the transfer function here, coherent transfer function, is 1 until we get to the cutoff frequency, and then it goes to 0. And its cutoff frequency here, f naught, is w over lambda z sub I. And if I think of a lens here of diameter 2w, I could write this as 1 over lambda f number. Well, that's the f number of the converging beam. So we have a lens here forming an image of something. Z sub I away. And the object was the distance z sub O away. And diameter of lens is equal to 2w. And so the f number of the converging beam is what I just call f number, z sub I over w. And so the cutoff frequency here goes as, I have a mistake here. It should be 2 lambda f number. Because the f number here would be z sub I over 2w. So the cutoff frequency there is 1 over 2 lambda f number for coherent light. Okay. That's the cutoff frequency in image space here. What would the cutoff frequency in object space be? The difference in frequencies just go as the magnification. So if I want to talk about object space, instead of this being a z sub I, it would be this distance, z naught. And it would be 1 over 2 lambda, whatever this f number is here in object space. Okay. Any questions? Well, it's kind of interesting the way this works. I mean, it's the transfer function is unity and then goes to 0. And so what I thought I'd try to do now is to draw a little diagram here. See if we can kind of get a little physical feel as to why this is what it is. Okay. So I'll do a physical explanation here.
If you're cut off, it should be 2W and then the 2.
No, this is coherent light. The cutoff is 1 over 2 lambda f number. When we get to incoherent light, it's going to be 1 over lambda f number. And the curve is going to be different. And we're going to have a little different physical explanation for that. And that's when I really can talk about lenses as being interferometers. But okay, let's talk here. We have coherent light. And kind of just a little physical description here. And let's say we have an object. Be something, just a grating, sinusoidal grating. 1/2 times 1 plus, give it unity contrast here, so cosine 2 pi f naught x. And this can be, you know, we can think of this either in object space, where this is the frequency of the object, or we can think of it in image space, where this will be the frequency of the image here. In fact, I guess what I do here, oops, I'll make that f sub x 0, where f sub x 0 is the frequency in object space, and f sub xi in image space. And again, the frequencies would just differ by the magnification. And so we know for this grating, nice grating, we illuminate it, we get just a 0 order coming out of it, and we get a +1 order, and we get a -1 order. And we know that if we take this grating and we illuminate it with a beam of light, that there's at least 3 orders. And if this angle is theta here, for small angles, this would be just lambda f, f sub x. And so in object space, that would be lambda f x naught. Image space, that's lambda f xi. Okay? So that's going to be the object for a system. It's just this grating. And now let's image this grating with our lens. Now, so here's our lens. And the lens has some diameter here, 2W. And object is over here. The distance z 0 away. Theta 0. And the image is over here someplace. Z sub I away. So this is theta sub I. And so theta naught, for this grating anyway, so this is light going into the grating and diffracted out, is lambda f sub x naught, or in image space we could say theta sub I is lambda, whatever the frequency is in image space. And if this light just barely goes through, so for low frequencies, the light's going to get through without any problem. until we finally get up here to some angle where the light just barely gets through. And that, for small angles, that will be at an angle of W over Z naught, or W over Z sub I in image space. And so the frequency for the cutoff object space is W over lambda Z naught. And in image space, that's W over lambda Z sub I. And so if we put this grating here at different frequencies, you know, as long as, so the zero order just goes zipping down here. The +1 order, as long as the angle is small enough it gets through the lens, everything is great. And then finally, when the angle exceeds this angle right here, the light no longer gets through, and so I don't image that spatial frequency anymore. And so that's why the transfer function here is just unity up to this point where the first order no longer gets through, and then transfer function goes to 0. Okay. And so all this, what this lens is doing is it's combining these. There's another beam that gets through down here, the other order. It's combining these three beams to produce an image of the grating. And when the grating frequency is so large that the light doesn't get through the lens, well, there's no image for that spatial frequency. So if our order doesn't get through, the transfer function is 0. As long as the order gets through, the transfer function is equal to 1. Maybe I should write that down. If order gets through, lens, transfer function equal 1. If order does not get through, lens, transfer function is equal to 0. Okay. Simple as that. Any questions? If not, I have to ask you a question. We haven't talked about aberrations and transfer functions yet, but let's make some comments here about aberrations and the coherent transfer function. Let's say this lens has some aberrations in it. Is that going to change my cutoff frequency? No, because the light still gets through. What will it change? It might change the image, because if I have some aberrations, the light for the spatial frequency it goes through where the aberrations are, we'll see a phase that it's not supposed to see. And so I'll still get fringes here, but the fringes will be shifted. So let's say I have something that has at the edge of the lens there's a little phase here, spherical aberration. So now the light going through the edge of the lens will see the wrong OPD, and when they interfere with the guy here, it's going to cause the fringes to shift. And so we haven't talked about it yet, but we will. There's a phase associated with the transfer function, and the phase is going to determine where that spatial frequency, the position of the spatial frequency here. So you might have a shift of certain spatial frequencies will be shifted from where they're supposed to be. And so that can also mess up your image. Okay. So you kind of understand coherent transfer functions. Well, let's start the incoherent ones, and then I'm going to quit early today because I want to hand out the exams. But let's at least start the incoherent transfer function. I find the incoherent transfer, the coherent transfer function is interesting, but the incoherent transfer function is extremely interesting, I think. And so let's go through that. 15.2. So transfer function of incoherent imaging system. And again, we're following Goodman here. So now the image here. So if we're talking about incoherent light, we have to talk about not amplitudes, but we want to talk about intensities, or Jim Palmer might say irradiances, I guess. But anyway, I'll call it intensities. That the intensity here of the image is some constant which we're not going to worry about. And now we're going to convolve the intensity point spread function. So that's h of u minus squiggle v minus eta squared, magnitude squared. So it's intensity point spread function. And now we have the perfect geometrical image intensity. Okay. So it's a convolution of the intensity point spread function. And so now when we talk about the transfer functions, we're going to be talking about the transfer functions for the intensity distribution. And so we have to again go through here and find the spatial frequency content of a perfect geometrical image. So g sub g, f sub x, f sub y is equal to, up here, we're just going to take the Fourier transform of the intensity distribution for the perfect geometrical image. So e to the minus I 2 pi f sub x u plus f sub y v du dv. And then we're going to normalize this by what we would get at zero spatial frequency. That's I sub g of u and v du dv. And so that's for the perfect geometrical image. And then we need to do a similar thing here for the real image we get. So I'll write that down, and then we'll stop for today, I guess. So for the real image here, the spectrum g sub I, f sub x, f sub y, is, well, same Fourier transform, except here we put I sub I of u and v, e to the minus I 2 pi f sub x u plus f sub y v du dv. And again, we will divide by what we have at zero spatial frequency. So integral of I sub I du dv. And so we have normalized to 1 at zero spatial frequency. Okay. And then maybe there's one more thing I can write down today before we break. is that, so this is the spectra of the perfect geometrical image, the real image, and then the next thing we should do is to write down the Fourier transform of the intensity point spread function. So that's Fourier transform of h u v squared, magnitude squared, e to the minus I 2 pi f sub x u plus f sub y v du dv, and divide by what we have at 0 spatial frequency. So it's just h of u v magnitude squared du dv, and we're going to call that script h of f sub x, f sub y. So what we'll do when we come back on Thursday is that we're going to go through here and again use the convolution theorem and to show that this is just what we're going to call the transfer function, the optical transfer function for an incoherent system. And we'll look at a couple of examples for that, without aberrations first, and then with aberrations. And then we'll go through the physical explanation of this so we can understand why the incoherent transfer function behaves the way it does. Okay, so that would be on Thursday. So what I want to do now is to hand out the exams, and I'll just repeat again that the average was 74, mean was 77, high of 100, low of 18. And again, for those of you who did not do so well on this exam, I'll tell you that, again, you know, anyone who gets an A in the final will get an A in the course. And so don't give up yet. Study hard. And I'll sip some coffee, and then we'll hand back the exams. And I think I'll turn off my microphone.